Hi everyone. In this video I wanted to go over some new ideas that have to do with using data from a sample to estimate something about a population. This is a drawing that I made of the Cal State East Bay campus in Hayward. Each of these stick figures is supposed to be a student at Cal State East Bay. We're going to imagine that all of these stick figures in this drawing make up the entire Cal State East Bay population. Obviously the actual Cal State East Bay population is much bigger, but we're going to pretend that this is the entire university population. And we're also going to pretend that we're interested in what the mean or average height of the student population equals at Cal State East Bay. We want to know what answer we would get if we were able to actually record the heights of all population members, add them, and then divide by the number of population members to get the mean height of the university. And let's say that we don't have enough time to actually give out a survey to every student at Cal State East Bay and record all of their heights because there's too many students, and it's either too difficult or too time consuming for us to do all of the work. So instead of recording the heights of all population members, we're going to find a sample of students at Cal State East Bay and record their heights, and then calculate the mean height of our sample. Then we'll use the mean height of our sample as an estimate or a rough idea of what the mean height of the entire university equals. And maybe we decide to go out and ask 4 students at Cal State East Bay what their heights are. 4 would be a pretty small sample size, but let's just use 4 as our example. So what if we end up finding this student right here, this student right here, and this other student right here? We would record their 4 heights, which are these numbers right here, and then we would add those 4 heights and divide the total by 4 to get the mean of our sample. And we'll actually calculate that sample mean together, but before we do that, I wanted to say that we're actually imagining that the mean height of the university is 60 inches. Now, as researchers, we don't know that the mean height is 60 inches, but we're saying that it actually does equal 60 inches. We just don't know that it equals 60. And this is also supposed to be the distribution of the students at Cal State East Bay. The distribution of their heights. So we can see that a lot of students at the university are shorter students who have these lower heights down here, and there's fewer and fewer taller students. So we're pretending that the mean height of the university is 60 inches, and that the heights at the university are positively skewed like this, in which there's a lot more shorter students and fewer taller students. This symbol right here is a symbol for a population standard deviation. It's called sigma. This symbol right here is the Greek letter mu. It's a symbol for population mean. We'll probably go over some of those symbols more later, but we'll just start by, I just want you to know these 2 symbols right now. So, like I said, we're pretending that the mean height of the university is 60 inches. We're pretending that the heights are positively skewed in the university with more shorter students. And we're also pretending that the standard deviation, or the amount of spread in the heights of the population, equals 8.36. So let's actually calculate the mean height of our sample. So we have to add these 4 numbers and divide the total by 4. so the mean height of our sample is 63.25. So we overestimated the population mean by a little bit because the mean of our sample is a little bit above the population mean. And in statistics, the symbol for a sample mean is an x with a bar above it. It's called x bar. It's actually called x bar. So let's put an x bar above our sample mean over here. This is saying that we took a sample of 4 people and our sample mean came out to 63.25. So let's record our sample mean right there. So this is the outcome of our study. We would say that the mean of our sample came out to 63.25, and that's our estimate of what the population mean equals. That's our estimate of the mean height of the university. Now what if we went out and did our study again, and we found a different group of 4 people? Well, we would probably get a different sample mean. And let's actually try it to see if we do get a different sample mean. What if when we repeat our study and we go out and we find 4 new students, we end up getting this student right here, this student, and this student right here. So we go out to repeat our survey and we record the heights of these 4 students, and then we calculate the mean of the sample. So the people in red were our first sample, the people in green are our new sample. To get the mean of our second sample, we have to add the 4 heights and divide the total by 4. And this time we got 55.75, which is down here. So what we've done so far is we went out and we did a survey of 4 students. We recorded their 4 heights, and then we calculated the mean of our sample, and we got this sample mean up here. Then we repeated our study. We went out and we found 4 other Cal State students and recorded their heights, and calculated the mean of that sample, and the mean height of the second sample came out to this number right here. So our first sample had a mean height of 63.25. Our second sample had a mean height of about 55.75. So what we're seeing right here is the idea of sampling variability. Sampling variability is the idea that different samples give different results. When you do a study with a certain sample of people, you'll get a certain result. And then if you go out and repeat the study with a different sample, you'll probably get a different result than you did the first time. Because different samples are different groups of people, and that's why different samples give you different results. If I kept repeating this study over and over again, sometimes my sample would include shorter students, and the sample mean would be lower. Sometimes my sample would include taller students, and the sample mean would be higher. But overall, most of the sample means would end up being most of the sample means that I would be recording would fall pretty close to 60, which is the mean height of the university. Every once in a while, it's possible that I might end up, if I kept repeating this study, every once in a while I might get 4 really short students. I might get 4 really tall students out here, and the sample mean would be very high. But that's not going to happen as often. the extreme samples won't happen as often. Now let's um, now let's imagine that when I go out and repeat the study again, that I can actually reuse a person who is in the sample the first time. I'm sorry, I can actually go out and reuse a person who was already surveyed in an earlier sample. So what if I go out this time and I end up getting this person right here, this person right here, this person, and this person, and now I calculate my sample mean. Well, these four people in the blue circles are going to probably have a sample mean. It's different than these first two sample means right here. So let's see what it comes out to. It's 60.5. So that sample mean is the most accurate sample mean we've had so far because it's very close to the population mean of 60. So we've talked about the idea of sampling variability, how different samples give different results. And because of sampling variability, some samples actually end up being more accurate than others. This sample was the most accurate because the mean height of this sample was very close to the mean height of the population, which we're trying to estimate. But these other two samples weren't quite as accurate because this sample underestimated the mean height of the university by just a little bit, and this sample overestimated the mean height of the university by just a little bit. Now that we understand this idea of sampling variability, I want us to talk about a new idea, which is called a sampling distribution. A sampling distribution is the, the collection of all possible outcomes that can be found when taking a sample of a certain size from a population. So like I said, the collection of all possible outcomes that might be found when taking a sample of a certain size from a population. So let's think about all of the different possible samples of four people that could be selected from this population. So now that we understand the idea of sampling variability, I wanted to talk about a new idea called a sampling distribution. A sampling distribution is a collection of outcomes based on all possible samples of a certain size. Now that we understand the idea of sampling variability, I wanted to talk about the idea of something called a sampling distribution. When you're taking a sample from a population, the sampling distribution is the collection of all possible outcomes that could be found. Now that we understand the idea of sampling variability, I wanted to talk about a new idea called a sampling distribution. When you're taking a sample from a population, the sampling distribution is the collection of all possible outcomes that you might end up getting. So, if I'm taking a sample of 4 people from this population, and I'm recording their their heights. There are there are many possible samples of 4 people that I might end up selecting, and each of those samples would have its own sample mean. So far, we've taken 3 samples and we've calculated the mean height of each of those 3 samples, but there's many other possible samples of 4 people who could have been chosen. For example, here's a different possible sample of 4 people who could be chosen, and this sample has its own sample mean, which is just the total of the 4 heights divided by 4. And this group of 4 people in purple would be a different possible sample. Notice how this person right here is inside the brown sample and the purple sample, but the possible samples of 4 people can overlap because as long as it's not the same group of 4 people, as long as it's not the same exact group of 4 people, it's considered a different possible sample. So these 4 people in brown, which are this person, this person, this person, and this person, are a different possible sample than the 4 people in purple. So if I went out and I selected 4 people to be my sample, I could get the 4 brown people, or I could get the 4 purple people, and they would be different possible samples. So if I went out and I selected a sample of 4 students from the university, I could end up getting the 4 people in the brown circles, or I could end up getting the 4 people in the purple circles. Those are just 2 different possible samples that could end up being selected. Each, if I'm going and I'm selecting 4 students, each possible combination of 4 people is a different possible sample that could be found. So even let's see, even this would be a different possible sample of 4 people. So what I did is I circled the 3 people in the orange circles, and then selected a different person here. And it is a different group of 4 people than the orange people, than the people in orange are. So it is a different possible sample of 4 people, and it would have a different sample mean than the orange sample would, because it's not the same exact group of 4 people. So I'm saying that each of these possible samples of 4 people has its own sample mean. So imagine all of those sample means in a graph like this right here. Now this graph doesn't actually exist, but just imagine that each of these sample means are inside of a distribution right here. So all of the possible samples of 4 people that have a sample mean of 60 are stacked right here. All of the possible samples that of 4 people that have a mean height of 57 would be stacked about right here. And all of the possible samples that have a mean height of 50 would be stacked here. And all of the possible samples of 4 people that have a mean height of 75 would be out here. So here, down here we have the samples of 4 people that have the lowest sample means. So they're the shortest possible samples. And up here we have taller groups of 4 people that have higher sample means. So if I ended up selecting 4 really tall students, the sample mean would end up being really high, and I would get a sample mean out here. If I ended up selecting 4 really short students, I would have a low sample mean, and that sample mean would be down here. But there aren't as many of those extreme samples in the population. Most of the possible samples of 4 people would have a sample mean somewhere in the middle. So I said that this distribution that we're talking about here is just made up of all of the possible samples of 4 people that could be chosen. So here's a group of 4 people that has a mean height of 50. This is in a kind of a shorter group of 4 people. Here's a possible sample of 4 people that has a mean height of 80. So it's 4 really tall students. Here's a group of 4 students who aren't really especially tall or short, and they have a sample mean in the middle. So all of these sample means have a distribution, and when I go out and I take when I actually do my study and I take a sample of 4 people and I record their heights and I calculate the mean height of my sample, what happens is I end up with one of these as my actual outcome, because I'm going to select one group of 4 people to be my sample, and I'm going to calculate the mean height of that one sample. In this curve, we have all possible samples of 4 people, and I'm only going to end up selecting one of them to be the actual sample. So if I select this group of 4 people, I guess my sample mean would come out to about 67. If I selected this group of 4 people, the sample mean would be about 50, and I would have a shorter group of 4 students, and my sample mean would underestimate the population mean by quite a bit. Or if I ended up with these 4 people in my sample, I would have a really tall group of 4 people, and my sample mean of 80 would overestimate the population mean by quite a bit. So what I have to do is, when I do my study, I just have to hope that I end up getting I have to hope that I get one of these more accurate samples, and that I don't get one of these more extreme samples. Down here we have the samples that have really low sample means that underestimate the population mean by quite a bit. Up here we have the samples with really high sample means that overestimate the population mean by quite a bit. And in the middle we have the more accurate samples that have sample means close to the population mean. And typically most of the samples do have sample means close to the population mean, and there's fewer extreme samples that have really high or low sample means. That's why the curve peaks out here. It peaks near the population mean, and it trails off as you go further away from the population mean, because there's less and less possible samples out here, and less possible samples out here. Now it's important to remember that this distribution that I'm showing here, the sample distribution, isn't something that a researcher actually creates or constructs on paper. The researcher doesn't actually calculate the means of all possible samples. So this is just an idea that exists. It exists in theory, but it's still an important idea because it's still important to think about how some samples underestimate and some samples overestimate and some samples are more accurate. And it's important to realize that there's fewer samples out here, and most of them in this more accurate area. Now, this sampling distribution is really just made up of a bunch of different numbers, or a bunch of different values. It's just that each of those values is a sample mean. Each value in this distribution isn't the height of an individual person, it's the mean height of a possible sample that could be chosen. This is the mean of one group of 4 people. This is the mean of one group of 4 people. This is the mean of another group of 4 people who all come from this population. And if I take a sample of 4 individual people from this population, and I calculate the mean of those 4 people, that sample mean that I calculate is just one of the values in this distribution. Now, all of the sample means in this distribution actually have a mean and a standard deviation. Because if this distribution is just made up of a bunch of values, a bunch of x bars, those x bars have a mean and standard deviation of their own. And it turns out that the mean, or the center point of the sampling distribution, is actually the same as the population mean. The mean of the sampling distribution is always equal to the mean of the individual population members. So the mean, or the average of all of these x bars is actually 60. And the symbol for the mean of a sampling distribution is mu x bar. So it's just a mu with an x bar subscript. And the sampling distribution has its own standard deviation. And there's actually a special term for the standard deviation of a sampling distribution. It's called a standard error. So the standard deviation of a sampling distribution is called a standard error. And the symbol for a standard error is sigma x bar. It's the standard deviation of the x bars. And it turns out that standard error is equal to the standard deviation of the population numbers divided by the square root of the sample size. Here we're talking about a sampling distribution of the means of all possible samples of 4 people. Each of these x bars is the mean of 4 specific people in the population. So that means that the sample size that we're dealing with is 4. If you took the standard deviation of the population and divided it by the square root of 4 sample size, you would actually get the standard deviation of all of these x bars for the you would get the standard deviation of the means of all possible samples of 4 people. So basically, the standard error measures how much spread there is to the possible samples that could be selected from the population. So if I'm taking a sample of 4 people from this population, and I'm calculating the mean height of my sample, the standard error actually measures how much spread there is to the means of all of the possible samples that might be chosen. I'm only going to end up selecting one of the possible samples, but the standard error measures how much spread there is to the means of all of the possible samples of 4 people that I might end up selecting as my sample. And I want the standard error to be low when I'm doing my study, because when the standard error is low, then the possible samples have sample means that are really close together near the population mean. So if the standard error is small, then all of the possible samples, or at least most of the possible samples, have sample means that are packed in close to the population mean. And that would mean that all of the possible samples, or most of the possible samples, are pretty accurate, and I'm likely to get an accurate result. If the standard error is high, that means that the possible samples are really spread out, or kind of really spread out from each other. There's some sample means that are really low down here, and there's some sample means that are really high up here. In other words, if the standard error is high, then there's more samples, more extreme samples that highly overestimate or highly overestimate, and that means that overall the possible samples, are less accurate, and I'm likely to get a less accurate sample. Now I want the standard error to be low, and the way there's actually 2 things that affect the standard error. One of them is how much spread there is in the population. When the population standard deviation is high, and the population members are spread out far from each other, then the means of the possible samples are also more spread out, and the standard error is bigger. So when the population has more dispersion, and the population standard deviation is bigger, the sampling distribution has more dispersion, and the standard error is bigger. That's because if the population members are a lot more spread out from each other with a lot more extreme people, then there's going to be a lot more extreme sample means. And but also, so like I said, when the population has more dispersion, the sampling distribution has more dispersion also, and the standard error is bigger. If you take a bigger sample size, if you take a bigger sample from the population, then the possible samples will have less dispersion, because larger samples tend to be more accurate. When you take a large sample from a population, the sample mean tends to be closer to the population mean and more accurate. So if you took a bigger sample, like a sample of 30 from this population, then each of those possible samples of 30 would have its own sample mean, and those sample means would be closer together, and they would be more packed in closer to the population mean with less dispersion. So let's actually look at an example of that. So let's just look at a possible sample of 30 people. 1, 2, 3, 4, 5, 6, 7, 8. Let's just imagine that I circled 30 people to be a sample of 30, and I record their 30 heights, and I calculate the mean height of my sample. I add the 30 numbers and I divide the total by 30 to get the sample mean. That sample mean will end up falling somewhere on this number line. For example, it might come out to 64. It's probably going to come out somewhere close to the population mean of 60. And this isn't the only possible sample of 30 people that could have been chosen, because there's many different possible combinations of 30 people that could be chosen from this population. And each of those possible samples of 30 would have its own sample mean. For example, a different group of 30 people might give me a sample mean out here. If that sample happened to include more taller people, another group of 30 people might give me a sample mean down here if that sample mean included more shorter people. But, like I said, if I'm taking a sample of 30 people from this population with a bigger sample size, the sample means, the means of those possible samples will be packed in closer to 60 compared to these possible samples of 4 people, because larger samples usually have a sample mean closer to the population mean, because larger samples are more accurate. So this sampling distribution will have a narrower shape with less spread to it. This was more spread out because it had samples that were less accurate. This had more samples that were less accurate down here and less accurate up here, underestimating and overestimating. Here, here the sample means are mostly closer to the population mean. So when I actually do my study and I take a sample of 30 and I calculate the mean height of my 30 people to estimate the population mean, one of these possible samples of 30 people will end up being my actual sample. For example, if I get this group of 30 people, my sample mean is about 57. Or if I get this group of 30 people, my sample mean is about 63. But when I take a sample of 30, you can see that I'm likely to get a more accurate sample mean than I would have with a sample of 4. Because when I take a sample of 30, overall, the possible samples have sample means closer to the population mean of 60. So here, select all of these possible samples of 30 people has a sample mean, and all of those sample means have a mean and standard deviation of their own. Just like up here, the mean of the sampling distribution is still the population mean. It still equals 60. That's true no matter what sample size you're using. The mean of the sampling distribution always equals the population mean, because the possible samples always have an average equal to the population mean. But the standard error is changed because the sample means are closer together. Now this standard error will actually be equal to the population standard deviation divided by the square root of our new sample size of 30. So this would give us the standard deviation of this distribution. This would give us the standard deviation of this distribution. And since this has more spread, the standard error will be bigger. Since this has less spread and it's more accurate, and the possible samples are more accurate, this standard error will be smaller. So this will be a bigger standard error. This is a lower standard error. So the standard error is smaller when either the standard error is bigger either when the population has more dispersion or the sample size is small. The standard error is smaller when either the population has less dispersion or the sample size is bigger. Now, if you're a researcher who's taking a sample from a population and you're calculating the sample mean to estimate the population mean, you can't actually calculate what the standard error is because you have to know what the population standard deviation equals to be able to plug that into the formula to get the standard error. And as a researcher, you don't know what the population standard deviation equals, because to calculate the population standard deviation, you would have to have data from the entire population, and you don't. So what we'll talk about later is how a researcher will can actually estimate the standard error rather than actually calculating it. Since I said it can't be calculated because you don't know what the population standard deviation is. But even if I don't calculate the standard error, I know that I want the standard error to be low because I want to be drawing from a distribution of possible samples that's accurate and close to the population mean, like this is. I know that the standard error will be smaller if I'm either sampling from a population with less dispersion or I'm taking a bigger sample size. So far we've talked about we've covered the idea of sampling variability and the idea of a sampling distribution. And I want you to realize that each of these x bars under this curve is just the mean of a different possible sample that could be chosen. So if I'm taking a sample of 4 people from this population, I'm calculating the mean height of my sample. One of these will end up being my actual sample. If I take a sample of 30 people from this population, and I calculate the mean height of my sample, one of these will end up being my actual sample. And we talked about how the mean of the sampling distribution equals the mean of the population. And we talked about standard error. We talked about how the amount of spread in the sampling distribution is predictable and it's measured with the standard error. Now I wanted to talk about how you can actually, when you're taking a sample from a population, you can actually predict what shape the sampling distribution has. The shape of the sampling distribution is predictable based on the shape of the population that you're sampling from and the sample size that you're using. And I'll show you a website that can do a demonstration of this. Here we have a website that can simulate sampling from a population, And in this box right here, we're looking at the values of all members of a population. It says that this population has 18,000 people, so maybe it could be a city that has 18,000 people, and each of these numbers over here in the left column is just the ID number of the person. So this is person 14,246. Each number over here is the sleep time of the person, or the number of hours of sleep that person is getting each night. So now let's pretend that we want to do a study in which we want to take a sample of this population, record the number of hours that the people in our sample are getting per night, and then calculate the mean of our sample to estimate the mean of the population. So we're going to give the people in our sample a survey that asks them, how many hours of sleep are you getting each night? And we're going to calculate the mean of all of the answers that were recorded from our sample to estimate the mean of the entire population. And if I click here, it says show sampling options, and it'll actually let me take a sample of this population. So let's say I want one sample of 4 people. It'll actually take a sample of 4 people, and it'll actually give me my data set. So this is just like if I had actually selected 4 people randomly from the population and given them a survey and recorded how many hours of sleep they're getting each night. So this is my actual data set that I've actually recorded from my sample. And if you add their four answers and divide the total by 4, you get the sample mean. And it tells me what the sample mean equals. It turned out that my sample mean was 7.313. And over here, it tells us that the population has a mean of 8 hours. So my sample mean was a little bit below the population mean. I underestimated the population mean by a little bit. Now this is meant to be just showing all population members, like the individual population members. So here we have people who are getting 4 hours of sleep. Here we have some people who are getting 10 hours of sleep. Here we have all the people who are getting 8 hours of sleep. But the mean of the population is 8. So the mean, remember that the mean is near the center of the population. So we can see that about half the population is getting less than 8 hours of sleep, and about half are getting more than 8 hours of sleep. So that's why 8 is the population mean, or the population average. These are the 4 people in my sample. It's their 4 sleep times, with the sample mean of 7.3 at the center of the sample. And this over here actually records my sample mean of 7.3 as a building block. This is the mean of my sample. Now, if I repeat my study and I take 4 other people, I'll get a different sample. And before I do that, I wanted to mention that this actually shows the 4 sample members inside of the population that they came from. So the 4 people in my sample were getting these amounts of sleep. Here's the 2 people who were getting 7.25 hours. Here's the person who's getting 8.25, and here's that person who's getting 7.25, and they're inside of this bigger population. And let's remember that the sample mean is the center point of the sample. So the center of these 4 people right here is about 7.3. That's why that's the sample mean. So the population mean is the center of this entire population. The sample mean is the center of the 4 people in the sample. Right here. Now I'm going to repeat my study and survey 4 other people. Looks like I got some bigger numbers this time. These people are getting more than 9 hours of sleep, so the sample mean should be higher this time. So these are the 4 people, and my sample mean this time came out to 7.7, and each time I do this, it records the new. Each time I take a new sample and I calculate the sample mean, it puts a new building block on here. So every building block is just the mean of a different sample that I've selected. So now I should have 2 building blocks. Now I repeat my study again. I take 4 other people, and I calculate the sample mean. And the third sample mean should be a third building block. So it's just recording more and more sample means. Now I'll take another sample. And each time I do this, you can see the 4 people inside the sample. You can see the 4 people from the sample inside of the population that they come from. You can see the 4 people by themselves here, and you can see the sample mean as the newest building block. Now all of these sample means that are being recorded on the right side are starting to form a shape as I repeat the study over and over again. And when I take more and more samples, I'm using up more and more of the possible samples, which means that as this builds up, it's getting closer and closer to the shape of all possible samples that I talked about earlier. As I use up more and more of the possible samples, you start to actually see the shape of the sampling distribution, which includes all the means of all possible samples that could be chosen of 4 people. And if the population has a normal distribution, the sampling distribution is always normal. And that's actually true no matter what sample size you're using. So if I'm taking a sample of 4 people from a normal population, all of my possible samples also follow a normal distribution. Now what if I wasn't taking a sample of 4? What if I was taking a sample of 30? Well, since the population is normal, the sampling distribution will still be normal. The means of all of the possible samples of 30 that I could end up selecting will still follow a normal distribution. And I'm not actually going to really see a normal distribution until I take enough samples. So if I'm taking a sample of 30 people from here, and I'm calculating the mean of my sample to estimate the population mean, remember that my actual sample that I actually end up selecting is only one of these building blocks. So I might end up choosing this group of 30 people and I might end up getting this sample mean right here of about 7.7, or I might end up getting these 30 people and getting a sample mean of about 8.3, or I could get one of these groups of 30. I could get this group of 30 people with a sample mean of about 7.8. So you could imagine that each of these building blocks contains 30 people inside of it, and it's stacked above the mean of that sample of 30 people. So these 30 people in this box have a mean of about 7. 30 people in this box have a mean of about 8.4. And if we start at a certain point, like this, and we go upward, we're up a certain column, we're just looking at different possible samples of 30 who all have the same sample mean. So, for example, this is 8.5. Here's one group of 30 people that has a mean of 8.5. Well, maybe 8.4. Here's one group of 30 people that has a mean of 8.4. Here's a different group of 30 people that has a mean of 8.4. And here's another group of 30 people that has a mean of 8.4. Down here, this is about 7.7 or 7.6. Here's one group of 30 that has a mean of 7.6. Here's a different group of 30 that has a mean of 7.6, and here's another group of 30 that has a mean of 7.6. So if I take a sample of 30 and I calculate my sample mean, my outcome will be one of these boxes. And I said that no matter what sample size I'm using, if I'm sampling from a normal population, the sampling distribution of possible samples is always normal. That's not true if you're sampling from a skewed population. So let's look at a skewed population right here. This population of 18,000 people is now positively skewed, meaning a lot of people are most people are at the lower end down here, getting less sleep, and fewer people are out here getting more sleep out here. It turns out that if a population is skewed, the shape of the sampling distribution depends on the sample size. So, if you take a small sample from a skewed population and you calculate the mean of your sample, what happens is the sampling distribution follows the same shape as the population. So since most of the population members are at the low end, most of the possible samples will also be at the low end with lower sample means. And fewer possible samples will be up higher with higher sample means. That makes sense because if there's a lot of population members down at the low end down here, then a lot of the combinations of 4 people will come from this low end and have low sample means. There aren't as many combinations that will give you higher sample means. We can see here that a lot of these combinations of 4 people are coming from this lower end. So if the population is sleep deprived, and you take a sample of 4 people from that population, you're likely to get a sleep-deprived group of 40 people who will end up having a low average. That's why most of the possible samples have sample means at the lower end. Now, if we kept on going, we would eventually, if I kept on sampling, we would start to see this this positively skewed shape of sample means. Sorry, I think it froze a little bit. Well, what we would actually see is that the sampling distribution is has less skewness than the population does, but it still follows the shape the population does, but it's not as skewed as the population is. It's more normal. Let's take 1,000 samples at a time. So it's like I've repeated the study 1,000 times. Yeah, now we're starting to see it. It's positively skewed, like the population, but not as dramatically skewed. One thing I like about this is that if you click on a certain sample, it lets you revisit the people in that sample. So this right here is the mean of these 4 people. This was the mean of these 4 people. This little building block here is the mean of these 4 people. And down here, that's the mean of these 4 people. So you can see that the sample mean is at the low end because these 4 people are at the low end of the population. These 4 people, since these 4 people have low values, they have a low sample mean. And here, since these 4 people have higher values, they have a higher sample mean up here. Now, one last point I wanted to make is that if you're taking a big sample from a skewed population, the shape actually of the sampling distribution actually no longer follows the shape of the population. If you're taking a sample of generally at least 30 from a skewed population, the sampling distribution will follow a normal distribution over here, even though the population is skewed. So if you're sampling from a skewed population, and you're taking a small sample size of less than 30, the sampling distribution is skewed, just like the population is. It follows the shape of the population. But if you're taking a sample of 30 or larger, the sampling distribution will be roughly normal, even though the population is skewed. So like I said, if the population is normal, the sampling distribution is always normal, no matter what sample size you're using. If you're sampling from a skewed population, the sampling distribution is skewed with a small sample size of less than 30, but is roughly normal with a sample size of 30 or larger. And one thing that's important for us to remember is that we talked about how the idea of a sampling distribution, we need to understand that sampling distribution isn't made up of the people inside of a certain sample. So it's not the distribution of people, of a group of people who were inside of a certain sample. What it is a distribution made up of a bunch of sample means. And it's actually a distribution that only exists in theory. It's not something that it's actually created or constructed by the researcher. When you hear the word sampling distribution, it's easy to think that it must be the distribution of the people inside of a certain selected sample. But it's not a distribution of individual people. It's a distribution of possible samples. And next time we'll continue to discuss the idea of a sampling distribution, and we'll talk about how if you're sampling from a population and a sampling distribution is normal, meaning the sampling distribution is bell-shaped, with most samples in the middle and fewer extreme samples, then in that situation, it's actually possible to calculate something called a margin of error, which and I'll give you a little bit of an idea of what a margin of error is. If I'm sampling from a normally distributed population, meaning a bell-shaped population, or I'm taking a sample of at least 30 from a skewed population, then I know that the possible samples that I'm drawing from in the sampling distribution, I know that the sampling distribution that I'm drawing from is normal in that situation. And what I can actually do is calculate a value called a 95% margin of error that tells me the distance from the population mean to the lower and upper boundaries of the middle 95% of the possible samples. I'm not going to tell you how to calculate the 95% margin of error right now, but it does have a formula. And what it tells you is the distance from the population mean to the lower boundary and the upper boundary of the middle 95% of the possible samples. Remember that this is made up of just a bunch of sample means because it's a sampling distribution. And these sample means that are in the middle 95% are the most accurate samples because they have sample means closer to the population mean. A sample down here would have a really low sample mean, and a sample up here would have a really high sample mean. So as a researcher, I would hope to get a sample from the middle 95% because that's the most accurate area where the sample means are closer to the population mean. And if I if I'm doing a study and I calculate the 95% margin of error, and let's say, and it comes out to 2.1, what that would be telling me is that when I take my sample from the population and I calculate my sample mean, 95% of the possible samples that I could choose, or that I might end up choosing, are within 2.1 of the population mean. 95% of the possible samples that I could get are in this area, somewhere between 2.1 below and 2.1 above the population mean. And this, as a researcher, that would be something that I would like to know, because that tells me that since 95% of the possible samples are in here, I have a pretty good chance of getting a sample mean that's within 2.1 of the population mean. So we'll continue to talk about this idea more in the next video. But now I just want you to understand that if you're sampling from a normal population, bell-shaped population, or you're taking a sample of at least 30 people from a skewed population, then the means of the possible samples follow a normal distribution, or at least roughly, with fewer extreme underestimating samples down here and fewer extreme overestimating samples up here. And since you know that the samples are normal, what you can do in that situation is calculate the 95% margin of error, which tells you the distance from the population mean that you're estimating to these two boundary points. The only situation in which you can't calculate the 95% margin of error is if you're taking a small sample from a skewed population. Because remember, if you're taking a small sample from a skewed population, the sampling distribution isn't normal. In that situation, the sampling distribution is skewed just like the population. So as a researcher, what you do is you actually, in most studies, you have to either be sampling from a normal population, or be sampling from, or be taking a sample of at least 30 if you want to be able to calculate this 95% margin of error.